Yes, it looks like it's working. 35. 35, 35, 35. 35! What are we on, 4-2?
Yeah.
Oh. If I just go past it? 35? All right. Quiet, please. Can't concentrate. That's too loud. I know. We're going to have to get rid of that. Yeah, there is. Throws me off my concentration. Straight highway, 50 miles long, connects cities A and B. 50. Prove that it's impossible to travel from A to B by automobile in exactly 1 hour without having the speedometer register 50 miles per hour at least once. Okay?
It is kind of a given.
Yeah, it is, but I'm not going to say that.
Prove that it's impossible to travel from A to B without.
Okay. Yeah.
All right. This is the instantaneous. This is the instantaneous. And the road connecting them is continuous. Thereby connected by a straight line, linear function. Well, it doesn't say it has to be a straight line, does it? I think I'll put a twist into it.
Straight highway.
A straight highway.
That takes all the fun out of it. All right. Linear function is differentiable. Therefore, there exists a C such that f prime of C equals the average, 1 hour and 50 miles. We're just saying that the road is continuous. It makes a linear function, and that's differentiable for all values. Oh, that's therefore. There exists C such that the derivative equals 50 miles traveled in 1 hour. So the instantaneous equals the average rate of change. That's by the mean value theorem. By the mean.
Basically, if the average is equal to 50, then the instantaneous must be 50 at some point.
No, at some point it has to equal 50, correct. Yeah. Yeah, by the mean value theorem. Now, to contrast that, this is an example of continuous points and data. If you contrast that with, say, something that's not continuous, let's say Sam. Let's say Sam throws a shot put 22 feet, and he throws a shot put 42 feet. That doesn't mean that at some point Sam had to throw it somewhere in between 22 and 32 for all those values. That's not continuous data. All right? So you have to remember, sometimes there's discrete data where you just know certain points, but this says it's continuous. If it's continuous, that means every value has to be accounted for. Okay? So that's the difference between discrete and continuous when you're looking at something like this. You think it's just odd that this just works out. But if you go to something where it has those steps or things like that, then not every y value is represented, so therefore there is no average that has to be met instantaneously. They're giving you problems that are easy to solve because you haven't known anything else yet. It's going to change as we get further into the course. Okay?
Just keep doing these.
Yeah, exactly. All right, anything else before I go on? 29 we did in class in your notes. Next.
Yeah, we did. Good job.
Anything else? Kylie Stewart. 31. We'll give it a shot. Oh, remind me, I have something to tell you later. Yeah, it's interesting. Can't, recording. E is focused. I don't want to lose her focus.
Yeah, right.
She is. All right, if f is a polynomial function of degree 3, ax cubed plus bx squared plus cx plus d. There. That's a cubic function. Prove that at most two numbers satisfy the conclusion of the mean value theorem. First of all, it is continuous because it's a polynomial and it's differentiable. It's a polynomial for all a to b. Just by the fact it's a polynomial, you know that to be true. So what is the derivative of this going to equal? 3ax squared plus 2bx plus c. And that is a quadratic. So if you have a quadratic, you have at most two real solutions. Probably a fundamental theorem of algebra or something. That you can't have any more zeros than the degree of the polynomial. So if it's degree 2, you're going to have at most two real zeros. You got one real zero, or you have no real zeros, but the question says prove that you have at most two real zeros. Remember, it's just a line of thought that I want you to put down, stringing some topics together to show that you see how it works. Okay? Generalize for degree n for any positive integer n. Well, if you have a polynomial degree n, then you'll have at most n minus 1 solutions. Because when you take the derivative, you subtract 1 from the exponent, correct? So if you have a fifth degree polynomial, you can have at most 4 solutions that make it work. Okay? Anything else?
Are you doing something new today?
Yes, we are. That's okay. You're going to love 4.3 because of all the word problems.
What?
In college, you call them applications. Hey, I just found out. Next semester, I am teaching pre-calculus. It'll be fun. Yeah. Parkland. Yep.
Oh my gosh.
Wait, our next section is graphing? Yeah.
You'll get to word problems.
And word problems. And
Well, I
word
hate
problems.
graphing because when your calculator.
Yeah. It's not quite like that.
Not quite.
Fine. Oh, wait a minute. Yeah. Come on, 7. All right. Now, these are all exact values, as you've seen, like sine of pi, cosine of pi, sine of pi over 2, cosine of 3 pi over 2, 1 zeros and negative 1. So I'll just write down 1 0 negative 1. You're going to be getting into the trig functions, and some of you didn't get a perfect 10 out of 10 when you got your checks back because you failed to notice that the sine of x equals 0 at pi. Okay? And also equals at 0 and 2 pi and 3 pi and 4 pi. Cosine equals 0, you know, pi over 2, 3 pi over 2, things like that. All right? You have to start to know these because you're going to be working more and more trig functions also. So there we go, a little rapid fire. Or just write down 1, negative 1, or 0. There are 8 of them. Don't write down 1 through 8. You won't hit your mark. Just, you know, make a left to right list or something. Here we go. 3, 2, 1.
I was like, 1 negative 1.
So,
Oh, man.
I know somebody got a 7 or an 8? Nice.
I got it.
Anybody get like a 0?
I got a 6. It's essentially a 0.
Okay. Not bad. We'll do this again later. We'll practice some more later. But you got to use those because you're going to be saying trig functions equal to 0 and you have to solve. So you have to know what they are. Also, we're going to be putting test points into derivatives. So you have to know what's positive and negative, 1, negative 1, things like that. Anyway, this is the first derivative test. It has rules, it has hypothesis, things like that. It will say on your final, it'll say on your test, use the first derivative test to do this. Use the first derivative test to do that. It's going to tell you. Just like with the mean value theorem, it had to be differentiable and continuous. The first derivative test helps you find max and mins, and it also helps you where the function's increasing and decreasing. Okay? That's mainly what it's used for, and you use a number line with it. Ready, Kylie? Ready, Ken? Ready, Ken. Nice! Here we go. So, what does that mean? When you want to draw a function such that the derivative is positive for all x. What does it mean when the derivative is positive? Yep, slope of the tangent line is positive. Positive means it goes up from left to right. If it goes up from left to right, that means your function's increasing from left to right. So, you could draw a line. You could draw a cubic. You could draw a square root, all increasing. So when the derivative is positive, that means the function's increasing. Okay? When the derivative is positive, that means f of x is going up. Okay? For example, if f of x equals, 3x, the derivative is 3. The line looks like it's going up for all x's, okay? These two symbols go together. The derivative positive, the function is increasing. If the derivative is negative, the function is going to be decreasing. We'll look at this one. Let's say f of x equals x squared. What's the derivative? 2x. If it equals 0, that means x equals 0 is a critical value. If you put a number on the left side of 0 in to the derivative, would it be positive or negative? Negative. If you put a number into the derivative from the right side of 0, would it be positive or negative? Positive. The parabola goes like this. So you can see that when the derivative is negative, the function is going to be decreasing. When the derivative is positive, it's going to be increasing. Okay? That's what this is trying to say. You're going to be making pictures like this, and sometimes the pictures get a little complex. For instance, we just had the parabola going the other way. If you had C, where the number equals 0, like in Rolle's theorem, it's going to equal 0. It's going to be a horizontal flat line. On the left side of this one, that's where the derivative is positive. The function is increasing. On the right side, where the derivative is negative. So we have a plus sign here and negative sign here for the derivative. Right here we have a 0. That is usually not going to be an answer. That's usually almost always an open circle. This is a consequence of the first derivative test. If I say, where is f of x increasing, over what interval, use x values to tell you where it's increasing. So f of x is increasing from negative infinity to c. Remember those from last year. You write your intervals. The function is increasing because the derivative is positive. The function is decreasing over the interval from c to infinity because the derivative is negative. Can it change? Absolutely. But just on this picture, this is where we're going. You're going to use your algebra to find c. You're going to use the first derivative test. Okay? You're going to put test points into the derivative, not the function. You put your test points into the derivative, not the function. The first week, people will ask, where do the points go? Into the function or to the derivative? The second one will say, he didn't come back? Oh. Sorry, E, I was talking to somebody about Josh Poulter. All right. And who? Oh, and Stephanie, I forgot. Chase who? He's got mono. All right.
Wasn't he here yesterday?
Yeah, it's a delayed thing. All right. So you put the test points into the derivative. How do you know? How do you know? Well, we'll go back to our example we just had. F of x equals x squared. F prime of x equals 2x. We had 0. If you put negative 1 into the function, it's going to be positive. If you put negative 1 into the derivative, it's going to be negative. You've got to put your test points into the derivative because we know the graph looks like this. So test points go into the derivative, not the function. Okay? And you all know the derivative is going to involve the product rule, the chain rule, the quotient rule, all those rules, so the functions are going to get a little bit more complex. Okay? And so are the graphs. All right, you ready? I think we got it. I think we're ready to go. Nice. Now this is obvious. If the derivative changes from positive to negative at c, then it's called a local max. That should make sense. If it changes, well, it could be a local max. It probably is a local max. Yeah. No, I'm trying to see if there's any like 1% chance it might not be completely ironclad. I'm trying to think. We'll take a look at it. If you have C, and you got the first derivative test is positive and a negative, that means on this side the function is going up, doesn't it? And on this side the function is going down, doesn't it? Well, that looks like a peak, correct? A maximum. Does it have to be the absolute maximum? No. That's why the word local means in the area. Okay? In the area of the graph you're looking at, locally, that's a maximum. It doesn't have to be a global or an absolute, but just a local. Okay? Anyway, and likewise, if it goes from the other way, if you have C and you have a negative and a positive, that means the function is going down. Here it means the function is going up. So that would give you a local minimum. Okay? I think that'll work. All right. I'm just checking everything. All right. Turn the static off. All right. So now we have our definitions for local min and local maxes. If it changes on both sides, local min or local max. If, however, you have a C that's a positive and a positive, where it goes up and goes up, C is still a critical number, but it's not a local max or local min. Okay? For instance, one thing you might have is f of x equals x cubed. You remember what that graph looks like? It goes from the third to the first. You know, it looks like that. If I take the derivative, f prime of x equals 3x squared. X equals 0 is a critical number. Yeah, if I put a number on the left side into 3x squared, it's going to come out positive. If I put a number on the right side of 0, it's going to come out positive also. So do you see how the graph is always increasing? But that's not a local max or a local minimum. Okay? All right? Excellent. Okay. We're moving on. So here, it doesn't tell you it's local max. So there's also those cases. Yeah, we just talked about that. If there's no change then there's no local extrema. So you remember when your problems you just did for today where it says show that or prove that? These are the words you're going to use, and that's how you're going to use it. The derivative is positive on both sides, therefore there's no local extrema. The derivative is negative on both sides, therefore there's no local extrema. All right? Yes?
So you said that the derivative of x cubed is positive on both sides?
Correct. 3x squared, that means it's always increasing.
Oh, because it's squared.
Right. Excuse me?
That's supposed to be out of C, or,
If the derivative does not change except at c, where it's going to equal 0,
right,
it won't have a sign at c. I mean, at c, the value is going to be 0. That's why you don't include it. Okay? Then it's not a local extrema. You ready, Grizz? Grizz is giggling. All right, moving on. Find the intervals. Grizz, focus, Grizz, focus, Grizz, focus. There you go. Find the intervals for which f of x is increasing and decreasing. Here's your equation. X cubed plus x squared minus 5x minus 5.
Bless you.
All right, Grizz is back. What's the derivative?
X squared plus 2x.
Very good. The derivative, 3x squared plus 2x minus 5. So those are critical numbers.
Bless you.
How do you find those, Matthew? Right, and use your quadratic program. What'd you get? What is it? 1 and negative 5/3. So those are the critical numbers. I factored it. You could have used the quadratic. Now those go on my number line. So I'm going to check on both sides, or actually all three intervals, for positive and negative. Okay, so I found them. Any questions so far about that? Okay. So, if I pick a number on the left side of negative 5/3 and put it into the derivative, what will come out, positive or negative? I'll pick like negative 1,000,000. Yeah, because the square is going to make it positive. That's the dominant degree. So that's going to be positive. And positive means that the function is increasing. If I put a number between negative 5/3 and 0 into the derivative, or 1, like 0, it'll come out negative. And then if you put like 10 or 20 or 30, it'll come out positive. It doesn't always work that way. Don't just assume that if you know 1, you know them all because they're going to alternate. That's not the case. If it were the case, we'd have a theorem that said that. So we got a local max at negative 5/3. We have a local min at 1. You have to find the y values. But in this case, it wants to know the intervals where f of x is increasing.
Read it. That was decreasing.
It is decreasing? I thought it was increasing. Both. We can do both. F of x is increasing from negative infinity to negative 5/3, and union 1 to infinity, right? I don't use brackets. I use parentheses. The book uses brackets. I don't. No, I use parentheses. Fine. And then it's decreasing from negative 5/3 to 1. See, I don't think a point can be increasing and decreasing. I think it's going to equal 0. So how's that? That is the first derivative test. Set the derivative equals 0 or undefined, find your critical numbers, put in test points in the derivative, see if they're positive or negative. Okay? So even if you graphed it out, you'd have to have all this work. Does that make sense? Good. What? That has no y values, so it's not a graph. It's merely a table of information. In stats, we talk about tables, graphs, and charts. Okay? All right. But you know that there's a local max and a local min right there. If you want to sketch a graph, you can type it into your TI. FYI. Some kids type in this and graph a parabola. You're not supposed to graph a parabola. You're supposed to graph the original function. Jeez. I know. There we go. That's the graph.
No, is that the next question?
No. All you got to do is just find the y values. Yeah, you just make a sketch. Well, it probably says sketch the graph. Look at that.
Can you go back to that last one, just really quick?
Sure.
Now you don't put in the derivative.
No, these are y values. They go into the function.
Okay, I'm out. I see that graph, please.
4027 is negative 8. Are the y values for your local max and local min? Okay.
Yes.
And now when you make your sketch, you know it's going to be a cubic. You know it's going to be positive, so it's going to look like that. You know it's going to have a y-intercept of negative 5. And there's all the, there's the intercepts. That's kind of cool. You learn that in pre-calc. Here's the minimum. There's the maximum. Both locals, don't forget they aren't absolutes. Oh, the second derivative test. Almost forgot. That gives you this point right there. Not yet. But see, there's more to learn. And then once you get the second derivative, you can label that point as well. I know. Look at that little eraser. I'm going to do that again. All right. Moving on. Oh, by the way, that was a point of inflection. Okay? Those PI numbers. Anyway. No, we're not done. We're moving forward. There's no been 5-minute warning.
No, yeah, practice stop at 1:30.
I got what?
Like 4 minutes.
Here we go. Let's try this one with the chain rule. X equals the cube root of x minus 5. Find the intervals for which it's increasing and decreasing. Probably have to make a sketch because this is part A. The graph, and label it with your local mins, local maxims. But first of all, you have to have the interval for increasing and decreasing. Did you take the derivative yet? No, you should be past it. How many x's are there in this one? 2. That means product rule, correct?
Yes.
Woo woo, product rule. How do you solve that? Yeah, then how do you solve it? Yeah, I was looking for a little bit more oomph. Excellent. Factor out. Oh, my little eraser. I wanted a little marker. Factor out. The x minus 5 to the negative 2/3. You've done that before. And I said when you're solving these, get used to factoring because you're going to be solving them. I said when you're taking the derivative. What's that going to give you in your first term if you factor out x minus 5 to the negative 2/3? Yeah, it's going to x minus 5 to the first. Plus 1/3 x. Ooh, then you can work with that. Yeah.
Would there be a chain rule in there for the x minus 5 and the negative 2/3?
There would be times 1.
Oh, yeah.
Okay? So, we're going to solve that. Now, the 5, is that a critical number? Is that in the domain of the function? Can you take the cube root of 0? Yes, you can. So 5 is a critical number. Or number, yeah, it's a critical number. And what else is there? 4/3 x equals 5. So that means x would equal 15/4. Is that right? Did you get that, Kylie Stewart?
Sure.
Nice. 5 and 15/4. 5 makes it undefined because it has a negative exponent. And the 15/4 makes the second factor equal to 0. Those are the critical numbers. Is 15/4 bigger than 5? I don't think so, because 4 times 5 is 20. So, I put those on the number line, and now I do my test points. This is not the sketch, this is finding intervals of increasing or decreasing. Very logical, very methodical. So if I put in 0, would this be a positive or negative result? Some people might like to look at it like this. The cube root of x minus 5 squared. If I just look at it like that. The bottom is always going to be positive, isn't it? So if I put in 0, the top is going to be negative. So that means the function is decreasing. Now I asked 15/4, somebody says like 3.75. So a nice number to put in is 4, don't you think? Well, 4, the bottom's always going to be positive. We established that because it's squared. So if I put 4 in right here, I have 16/3 minus 5. Positive. Nice. Now if I put in 102, a number bigger than 5, I just chose 102.
I think it's going to be positive.
Positive. So not too much happening at 5. It's not a local max or local min. However, when you write your increasing, you can't include that. Remember? There's open circles here. So you have to have a union symbol for the increasing part. Yes?
So I just got continuous or no?
Yes.
But I have holes in it.
No, they have holes in the intervals for your solutions. Because at 15/4, the derivative equals 0. That means the function is not increasing or decreasing, it's just hanging out. All right? Kind of like jumping on a trampoline. You jump up and you jump down. But when Taylor Ehman stops jumping up and jumping down, there's that moment where you're like, weightless. Remember that feeling? You don't remember that feeling at all?
I don't.
Have you ever jumped on a trampoline?
Yeah.
You jump up and you jump down. You remember that point when you're looking at someone and their hair is kind of like halfway? That's here. Can't have that. 5 minutes, we'll better hit the clicker. You'll be mad. And Stephanie and Chase. Ready? Clicker. So the function's increasing from, again, that should be parentheses. 15/4 to 5 and 5 to infinity would be increasing. Oh, she's got this. Decreasing would be, again, parentheses, negative infinity to 15/4. All right? Got that? Just sketch a quick graph. You can use your calculator for that. Yeah, a quick graph. I am clicking the button. Calculate the y values, and there's the graph.
That is odd.
Yeah,
That is. Okay, well that's what I got.
those are the y values. Wait, that's the wrong one, isn't it? That's the wrong equation. It's supposed to be x times x minus 5 to the 1/3. I just copy and pasted.
Support group.
That wasn't even the last one. Yeah. It was 3.
That's the derivative. That's the function value. There's your graph. There's the minimum right there. Perfect. I think that's it.
I can't hear. Oh my.
We'll worry about that later. There we go. 190, 1 through 15 odd.
Do it.
Let me stop the recording.